Day 28 of Chapter 4 introduces you to two new, very important and very straightforward theorems. The first is called the second fundamental theorem of calculus, and what's changing here is that now we have a function as one of the values in our antiderivative. So what this says is that if you take the derivative of an antiderivative, since those are inverse operations, they're going to cancel each other out, but first you would need to substitute this function into the inside function of your antiderivative. So writing this out the long way, using the fundamental theorem of calculus, the inside would become capital F of x minus capital F of a. But then when you take the derivative of these capital functions, you're back to your lowercase f functions. So I'm going to have f of x, but the derivative of a constant, when I take a and plug it into the function, I'm just going to get a number, is 0, so that second part disappears, and you're left with just this statement here, okay? Now, one thing that's very important to notice is that because we're taking derivatives, if the bound of your integral has a function more complicated than this, just plain x, you're going to need to take the chain rule at the end of your answer, and you'll see an example of that in a second. So to summarize, a definite integral is when you have numbers at either end of your antiderivative limits. This will produce a number as an answer, whereas if you have a function as one of the limits of your antiderivative, then your output will be a function. Related to that is something called the net change theorem. If you take the antiderivative of a rate, and notice that it says capital F prime here, the antiderivative of a rate, a bounded integral, will produce two amounts. And the difference between those two amounts is called the net change. In other words, if A is the starting point, then F of A is the starting amount. If B is the end point, then F of B is the end amount. And the difference between the end amount and the starting amount is called the net change. And again, you'll see an example of this in a couple slides. So these next two examples, I'm just going to walk you through. You don't need to practice these on your own. Things that I'm going to highlight for you are this and this. So in the first one, what we have is f of x is the antiderivative of this statement here, and then you're asked to find f prime of x. So if I need to take the derivative of capital F, I need to take the derivative of this antiderivative, and we invoke the second fundamental theorem of calculus. A derivative and an antiderivative essentially cancel each other out. I'm going to substitute x into this function here. I'm going to get x squared minus 2x, and we're done. That's all we need to do. Notice that x, the derivative by chain rule of x, is just 1, so there's no reason to modify this any further. For the second example, same situation. Capital F of x is this antiderivative statement. The first derivative of capital F is the derivative of this antiderivative. Again, derivatives and antiderivatives cancel out because of the second fundamental theorem of calculus. But after I substitute in 1 over the substitution cubed, which is 1 over x squared cubed, I need to perform the chain rule on this function here because we're taking a derivative. So that gets multiplied by 2x. So simplifying this, you get 2x to the negative 5. So those are the two cases of the fundamental theorem of calculus. One where your substitution is just a plain old x, and another one where your substitution will lead you to a chain rule step at the end. So now we're going to combine a couple things that we've talked about before, which is velocity functions and its relationships between derivatives and antiderivatives. You're given a velocity function that looks like this. It's valid from t equals 1 second to 5 seconds, and you're asked to find the displacement and the total distance that a particle travels. These two things are often confused, so it's worth our time to spend a little bit of review time. S of t is a position function. The first derivative of a position function is a velocity function, and that's what we were given here. We were given a velocity function. And the second derivative of a position function is the first derivative of a velocity function, which is an acceleration function. Going the other direction, the antiderivative of acceleration is velocity, and the antiderivative of velocity gives you displacement. Because you're going to plug in numbers for the bounds of your velocity, you're getting the difference between your starting and your ending points, and that's again by the net change theorem. If we want the total distance traveled, I need to take the absolute value of that velocity function and then take the antiderivative of that, and that gives you the total distance. So we're going to be using this first and second statements to answer these two questions in part A and part B. So first one, displacement. Take the antiderivative of your velocity function. You get a position function. If I plug in 5, that gives me my ending position. If I plug in 1, that gives my starting position. The difference between where I end and where I start is negative 18.6, but that's my displacement. And what does that mean? that means that I finished, or the particle finished 18.6 units left of its initial location. Because it's negative, your displacement, or where you're finished, is 18.6 units left of its initial location. This is not the starting and ending point. Those are contained up here before you do the calculations. So to see the second part, total distance traveled, I need to take the antiderivative of the absolute value of the velocity function. So we did this earlier as well. The antiderivative of an absolute value you got to be a little bit careful with. I plotted that velocity function, found out that the roots were at 4 and -3. It's a parabola with a y-intercept of -12. So I sketched the parabola and said that in order to define the total distance, I need the absolute value of that parabola. So anything that was positive in the parabola stays positive. Anything that was negative gets flipped to the positive side. So what was -12 becomes a +12. And then anything that was positive stays positive. And the question said find the area under this from 1 to 5. So at 1 to 4, I'm going to be using one function, and then from 4 to 5, I'm going to be using a different function. From 1 to 4, what I need is the opposite of my velocity function, because the blue was the original, the blue dashed. I need the opposite of that. So from 1 to 4, I'm taking the opposite of my velocity function, and then from 4 to 5, I'm keeping the original function because it originally was positive. Crank through all these calculations, you get 26.3. That represents the shaded area, and the shaded area under a velocity time graph is total distance traveled. So what you're looking at here is going to be a video of the particle moving. The velocity function was typed into Desmos. I took the antiderivative to get the position function, and then I hit a couple of things to make it plot a point. A is really the time. The Desmos has a strange thing where I can't get this t to be t, but A equals 1 at the time. So I'm going to start at 1 second, and I'm going to end at 5 seconds. And if you notice, when A is 1, my position is a little bit left of -12. If you plug 1 into this function, you're going to get -12 minus a half, which is -12 and a half, plus a third, which I believe is a little bit past -12, or -12 and -12 and 1/6, which makes sense for that. All right, when I play the function, the particle starts moving, and when it hits that blue dashed line, I can't pause it. Okay, so I guess I can't pause the video, but what happened was this blue point hit that blue line at 4 seconds. And I'll play it again in a second, but it's going to hit this blue line at 4 seconds. That represents when the particle stops traveling left. So the velocity was negative, which means it's traveling left. And at 4 seconds, when it turned from traveling left to right, its velocity for an instant was 0. Once it started traveling right for the final second, t equals 4 to t equals 5, traveling right is a positive velocity. So the starting point was -12 and 1/6. The ending point is right about here at a -31, and the displacement, or the difference between those two, is -18.6. So watching one more time. Four, it's at there. So the last slide here is an example of the net change theorem. Water flows from the bottom of a storage tank at a rate of 200 minus 4t liters per minute. That's important. That's a rate. If 3,000 liters have flowed from the tank after 1 minute, that sounds like a starting amount. Find the number of liters that have flowed after 6 minutes. So we're given the amount in the tank after 1 minute, and we're asked to find the amount in the tank after 6 minutes. How do I find an amount? The antiderivative of a rate is an amount by the net change theorem. So here's my rate function. I'm going to take the antiderivative of the rate, and I'm going to get A6 minus A1. To find the final amount, A6, I'm going to bring A1 to the other side and say that the final amount equals the starting amount plus the antiderivative of the rate. The antiderivative of a rate is an amount. So start at 3,000. Antiderivative, substitute in your boundaries, 6 and 1, you get 3930 liters. So after 6 minutes, 3930 liters have flowed. Final thoughts on the fundamental theorem of calculus and the net change theorem. Don't get caught up in the notation. They write it out different ways at different times. The The antiderivative of a capital F is a lowercase f, but the antiderivative of an f prime, the antiderivative of a rate, is just capital F. Okay. You'll notice over here I did the antiderivative of rate equals a, the antiderivative of r equals a, the antiderivative of a rate equals an amount. That's the important thing to know. What your notation, they'll use different notation in different spots.